I welcome you back to your YouTube channel. In this series on algorithms, analysis and design, we will be taking up another problem on Master's theorem. Okay, so this is going to be the fourth problem that we will be considering. So in this question, we are given a recurrence equation that is of the form Tn is equal to Tn by 3 plus Tn by 6 plus theta of n raised to the power root of log n. Okay. So now we are having two sub problems, one of the size n by 3 and another of the size n by 6. And in addition, we have got this additional term. Now, one thing that we have to understand is, first of all, we have to convert this form into the standard form. Now in the standard form, all the subproblems are going to have same size, that is n by b, and there will be a such subproblems. However, when we observe our recurrence equation, we find out that in our recurrence equation, the two problems are of different size. One is of the size n by 3 and another is of the size n by 6. So now we have to apply one trick. And what is that trick? The trick is very simple. We know that the n is going to be very large, and in this case the problem that is of size n by 3 is going to be larger. This problem will be bigger compared to the problem of the size n by 6, which means this bigger problem will be playing a dominating role in affecting the time complexity for the equation, right? So what we will be doing is we will be replacing this Tn by 6 term with Tn by 3 term. Why? Because this is a smaller problem, so the overall time complexity of the problem will be governed by the term that is higher in magnitude, or with the problem that is having a higher size. Okay, and we know that Tn by 3 is the problem with a higher size. So instead of n by 6, I will be replacing this n by 6 with n by 3. So Tn by 3 plus Tn by 6 happens to become Tn by 3 plus T n by 3. Okay, so with this substitution, what we come up with is a recurrence equation of the form Tn is equal to 2 times of Tn by 3, because now Tn by 6 has been replaced by Tn by 3. Okay, so 2 times of Tn by 3 plus theta of n raised to the power root of log n. Okay, so this is my modified recurrence equation after we have converted it into standard form by this substitution. So this was the substitution that we did, and as a result we are here with our recurrence equation. Now if I compare this equation with the standard form, we can always get the values for the coefficients a, b, k and p. Okay, so by direct comparison what we find out is that the value of a is equal to 2, the value of b is equal to 3. In a standard form, n is raised to the power k. So in this case, the value of k will be equal to root of log n, and n multiplied by root log n multiplied by root log n can always be written as n raised to the power root log n multiplied by 1. So instead of 1, what I can write? I can write log n raised to the power 0. Okay, so that means the value of p will be equal to 0. So with this, we come to the end of step 2, where we have found out the values for the coefficients a, b, k and p. Now we have to find out if these values actually conform to the settings, the different constraints. Okay, so the constraint says that value of a should be greater than or equal to 1. In this case, the constraint is satisfied. Value of b should be greater than 1. In our case, it is equal to 3. That means this constraint is also satisfied. Now for a large value of n, log n will be a positive number and root of log n will also be a positive number. Okay, that means in our case, this value will be greater than or equal to 0. So third constraint is also satisfied. And lastly, we have p is equal to 0, and the constraint says that the value of p should be a real number. So that means all these four constraints are satisfied by the coefficients, right? That means now it is possible for us to solve the problem by using Master's theorem. So remember what we do in the next step, we find out a and we compare it with the value of b raised to the power k. So we have already found out the value of k, which is found out the value of a, which is equal to 2, and b raised to the power k is equal to 3 raised to the power root log n. Okay, so for large value of n, this quantity will always be greater than 2. In general, this quantity will be greater than 2, right? That means a is less, in this case a is less than b raised to the power k, right? So this is what I have written. A is less than b raised to the power k, which means this is a problem corresponding to case 3 of the master's theorem. And then when the problem is in case 3, we will identify what is the value of p. So in this case, the value of p is equal to 0. So accordingly, the time complexity for this recurrence equation can be written as theta of n raised to the power k multiplied by log n raised to the power p. So in this case, I will simply be putting the values. What is k? K is root of log n multiplied by log n raised to the power p. And what is p? P is equal to 0. So this brings our time complexity to be equal to theta of n raised to the power log n. And this is going to be our answer. So if I recap, there are two tricks that we have applied in this problem. First of all, we had problems of different sizes. So if you have problems of different sizes, we are going to consider the problem of a larger size, because the problem with the larger size is going to play a dominating role in the computation of the time complexity. So the n by 6 term has been dropped, and instead of tn by 6 term, we have simply replaced it with tn by 3. This was the first trick that was used in order to convert the recurrence equation into the standard form. Additionally, we know that for a large value of n, this and root log n will be greater than, will assume a very high value. So when we were to compare the value of a with b raised to the power k, we have taken this into consideration, and that is why we have reached to the conclusion that for large values of n, a will be less than b raised to the power k. Okay, so these are the two tricks, or these are the two substitutions that we have made in order to get to a standard form that is solvable by Master's theorem. And once we are able to find out the case to which it belongs and the subsequent subcase, we are in a position to get the time complexity for the recurrence equation. So I hope you have understood the different steps that I have followed. In case you have any doubts, feel free to put it in the comments and I will be happy to answer. So with this, we come to the end of this problem.